Hello, dear students. The motivation of deliberating this video on Schrödinger and Heisenberg picture in quantum mechanics is basically to bring in an overview of these two mathematical pictures that consistently arise while doing foundation courses in quantum mechanics. And certainly this video will provide it will provide a fundamental overview of Schrödinger and Heisenberg picture, and for more detailed study one might explore some specific problems or examples or example calculations and advanced topics such as interaction picture or quantum field theory applications. So to start with, in quantum mechanics, what we have is we have the Schrödinger and Heisenberg picture, and they offer different perspectives. Basically, they offer different perspectives on the evolution of quantum mechanics. But at the same time, both approaches they are mathematically equivalent. These both approaches are mathematically equivalent, but certainly they differ in how we handle the time evolution. The time evolution. Now, to start with, let us first talk about the Schrödinger's picture, and to define Schrödinger's picture. In Schrödinger's picture, we have a state vector, uh, or we may call it a wave function as well. And this state vector or a wave function, it evolves with time according to the Schrödinger's equation. It evolves according to Schrödinger's wave equation, and the operators that are representing the observables, these operators are time independent. So the operators we have to choose as independent of time, and the state vector, the wave function, is going to evolve with time in accordance with Schrödinger's wave equation. So in Schrödinger's picture, if I have to write down the state evolution, so I'm going to write down the Schrödinger's time-dependent equation, and the Schrödinger's equation here, what it does, it governs the time evolution. It governs the time evolution of, say, some state vector. Let me choose that state vector as psi of t. So if I write down the Schrödinger's equation here, that is IH cross tau by tau t of state psi of t is nothing but h psi of t. So this is our Schrödinger's picture, and we call it the state evolution. Here we have h cap as Hamiltonian operator. So this h cap is Hamiltonian operator. Now, in Schrödinger's picture, when we talk about operators, I mean, if I have an operator, say, for the sake of argument, if I choose an operator a cap, this a cap, it does not depend on time. So I can think of this operator a cap of t is simply a, because it does not depend on the time. And the solution of the Schrödinger's equation that we have written down here is what we have is for time independent Hamiltonian, the solution to the Schrödinger's equation. So if I write down the solution of Schrödinger equation for time independent Hamiltonian, so Hamiltonian operator, it's time independent here. This has to be kept in mind. So the solution will be the state of psi as a function of t is e to the power of minus I h cap t by h bar state psi from 0. So, so this is the solution for the Schrodinger's equation in Schrodinger's picture. And the operators in this case are explicitly independent of time. Now, if I take an example of, say, if I choose an example of free particle. Now, let us assume that we have a free particle. If it is free, there's no external force acting on it. The terms arising from potential are 0. So I write down its Hamiltonian as P cap scat by 2m, where P cap is momentum operator and m is the mass of the particle under consideration. So we have taken a free particle, and the Hamiltonian for this free particle is p squared by 2m, where this p is the momentum operator and m is the mass of this particle. Now let us find the time evolution of the wave function, and assuming the initial state. So if I write down the initial state of this this free particle at psi of 0, what is that? That's 1 by under root of 2 pi sigma square e to the power of minus x square by 2 sigma square. So what we have, we understand this is a Gaussian wave packet. Okay, so what we are trying here is we have written down the initial state for the time evolution of this wave function for a free particle. And what we have time evolution operator. Time evolution operator e to the power of minus I h cap t by h cross. And this is going to be equal to e to the power of minus, for h is the Hamiltonian operator, and Hamiltonian operator is nothing but p cap whole square by 2m. So I can use here minus I p cap square by 2m h cross and t. Now what is important here is that since the momentum operator that has appeared here, this momentum operator in position is represented as p cap is minus I h cross tau by tau x in 1 dimension. And we can apply the time evolution operator to the initial wave packet here. So we can write down the solution as, say, psi of x and t is 1 by under root of 2 pi sigma square integration from minus infinity to plus infinity e to the power of minus p cap square t by 2m h cross e to the power of I px by h cross 1 by under root of 2 pi sigma square e to the power of minus x square by 2 sigma square dp in the momentum space. So this is an example to mathematically understand that when we choose the Schrodinger's picture, how we deal with operators, and operators are to be chosen as independent of time. Now talking about another picture which is called Heisenberg's picture. Heisenberg picture. Now let me define this Heisenberg picture. I mean, in Heisenberg picture, the state vectors are fixed. The state vectors are fixed, and operators evolve with time. In Schrödinger picture, the state vectors were not fixed, but and at the same time the operators were assumed to be independent of time. But in Heisenberg picture, what we have is that the state vectors are fixed and operators evolve with time. So the time evolution, so how do we write the time evolution in Heisenberg picture? The time evolution, say we have an operator A of t. The time evolution of this operator A of t is, it's u dagger A cap u of t. Okay. And this u of t is a time evolution operator here, and this operator is e to the power of minus I h t by h cross. And the state vector, I mean, the state vectors in this picture does not evolve. And we can see here that this u of t is a time evolution operator. It's a time evolution operator. But talking about the state vector in this case, the state vectors do not evolve. That means the state psi at time t is equal to the state psi at 0 time. And we can write down the time evolution of the operator. I mean, we can write down Heisenberg's equation of motion using time evolution of operator A of t. So Heisenberg's equation of motion. What's that? That's t by dt of A of t is I by h cross, the commutation between the Hamiltonian operator and the operator A that's dependent on time t, plus dou by dou t of A of t. So this is my Heisenberg's equation of motion, and I've defined the Heisenberg picture, and its definition goes back that the state vectors are fixed in solving those problems, and operators evolve with time. Now we can choose the same example for, say, for example, I choose the free particle. Now I choose the free particle, and if I choose the free particle, then I can think of the Hamiltonian operator equal to p cap squared by 2m. Now to find time evolution of the position operator, say x of t, and momentum operator, say p of t. So what we do here is, using Heisenberg's equation of motion that I have written down here, this is my Heisenberg's equation of motion. What can I write down? I can write down d by dt of x cap of t is equal to I by h cross, the commutation between the Hamiltonian operator and x as the function of t. And the commutation between h and x, we know Hamiltonian and x cap, what it yields is p cap by m. So the commutation relation between the Hamiltonian operator and the position operator is simply p by n. For a free particle, it can be proved as simple as possible, as we understand how to calculate the commutation relations between two observables. So in doing that, so what will be dx cap of t by dt? This will be p cap at 0 of t divided by n. So this is our Heisenberg's equation of motion for this free particle, and we can integrate this equation, and assuming that the initial position is x of 0. So if we assume that the initial position is x of 0 and we integrate this equation, what we will get? We will get x cap at some time t minus x cap at 0 is equal to p cap of 0 of t by m. Now, talking about the momentum operators, since momentum commutes with Hamiltonian, so if momentum commutes with Hamiltonian, then we can say, so regarding momentum operator, what we have, this momentum at some time, it commutes with Hamiltonian operator. So we can immediately think of the derivative of P of t by dt, which is I by h cross h P of t. This is because Hamiltonian commutes with the momentum operator, this must be equal to 0. So here we can say that P cap of t is equal to P cap of 0. Now, let us compare the two situations. I mean, what we have is we have two pictures. One is Schrödinger's picture, and another is Heisenberg's picture. And what we endorse here, what are the differences here, is that when we talk about time evolution, in case of Schrödinger's picture, the state vector evolves with time. It evolves with time, but operators are fixed. So the state vector, if I choose the state vector psi of t, it evolves with time in Schrödinger's picture, but operators, say a cap of t, they are fixed. They don't evolve with time. And in Heisenberg's picture, operators evolve. That means the operators, they evolve with time, but the state vectors, say psi of t, they remain fixed. Now, what could be the possible applications and usefulness of these two different mathematical approaches? If we talk about Schrödinger's picture, I mean, in case of Schrödinger's picture, I can say that it's often simpler, for solving time-dependent problems. Schrödinger's picture is it's good, and it's simpler for solving the problems in which we have which are basically time-dependent problems, especially with time-independent Hamiltonian. This is the most important point, with time-independent Hamiltonian. And this is what can be said about the application of Schrödinger's picture. And Heisenberg's picture, talking about the Heisenberg's picture, it's useful for problems that are involving the time evolution of observables, and deriving the relations involving operators. I mean, obtaining the relations that involve, I shouldn't call them operators, I should call them operator commutations. So we can summarize this video by saying that in Schrödinger's picture, the wave function or the state vector evolves according to the Schrödinger's equation, while operators they remain constant throughout a process, throughout the phenomenon. But in Heisenberg's picture, the operators evolve with time. They evolve with time according to Heisenberg's equation, while state vectors are taken as constants. And to be precise here, both pictures, either Schrödinger's picture or Heisenberg's picture, they are fundamentally equivalent, and they provide the same physical predictions. And the choice of picture basically depends on the specific problem, and which approach simplifies the calculations for solving the problem. So with this, I would like to end this video.